Alrighty, let's get started. So welcome to lecture two. I'm going to keep counting till I lose count. But today we're going to cover a little bit of what we missed last time, and then we'll start thinking about how to construct a robotic system. And so let's do a little bit of history and background into what a robot is, right? So um, robots were first defined in like 1920 in the 1920s by this Russian playwright, uh, Karl Kapek, and they're supposed to be things that help you do unpleasant drudgery and labor. But from there, like around the 1920s, that was the first humanoid robot. You see, it's basically a switch box with a bunch of cardboard around it, and it like the arms can move like that, but that's basically it. You kind of move from there to here where the robot can sit and stand, but they basically do nothing else. So just like some servo motors hooked up to do one motion. Then you went to this robot, which is pretty iconic. It looks kind of silly, but it's called the Unimate. It's one of the first industrial robots. And from there, we are now, or like we went to the next wave of robots, which took Unimate to Unimate Plus Plus and deployed it in a bunch of factories around the country doing manufacturing. But then we went to robots that are more familiar. So this one is called Shuki, came out of Stanford in the 60s. And that led to a lot of the algorithms we're going to talk about in this class. It basically is the first robot that is meant to reason intelligently about the world. So it is like trying to navigate around the building, but reason about its surroundings from its own sensor. But that led to a lot of the search algorithms and planning algorithms and sensor algorithms that we're going to deal with in this class. Right? And then you've probably seen these ones. These are the Honda P series. So Honda had a big program on humanoid robots in the late 90s. So the P series is the precursor to the Asimo, if you've seen the Honda Asimo, and the Asimo is the precursor to all the Boston Dynamics and all the humanoids of today. Right? So that is kind of the first wave. When the robots of today look a little more like this. Right? So on the top left, you have this everyday robot program from Google, where they wanted to put robots into every single Google office to sort trash, to retrieve items, to clean things up. You all have probably seen this. We were just talking about this. This is Atlas. This is a couple of generations old, but using a lot of similar techniques to what we're doing in this class. You can do things like parkour, and we've talked about Waymo, deploying with, again, a lot of planning, a lot of sensor fusion, a lot of control algorithms that we can discuss. Right? So it's kind of cool to see the evolution from that switch box to the robots we have deployed today in like less than 100 years. So that's all right. But to kind of give you the gamut of where these robots are applicable, they're applicable in industry, they're applicable in outdoor navigation, things like inspection, disaster relief, search and rescue, delivery, and also in home and office manipulation. So we'll kind of rush through this real quick, but I think it's fun to look at like what the applications are. So these are two from Amazon. Has anyone been to an Amazon fulfillment center? They're kind of interesting. Sid will tell you a lot more about it, but basically they have these pods. There's actually one in the robotics lab, and the pods have items in each of these like little cubes, right? And rather than people moving to the pods move to the people. And so people stand in different places, and then the pods are on these moving robots, and the robots just move to the different people. And so the hardest part of this operation is not the moving, it is the picking. And so they still have people do a lot of the picking, but people stand in place, and then the pods move from place to place. And so the hard problem then is that if I have like 1,000 of these or 10,000 of these, and they're all navigating at once, like how do I find a collision-free, efficient path for all of them? And then that's largely hand picking, but then they've kind of been building newer stuff. This program called Sparrow, which is trying to automate like package handling. So they have pods like that with totes, and they're trying to like pick and place items. So you can see here that they're not using like hands, but rather suction cups, because suction cups are just way more reliable, way faster throughput. And this system is handling millions of picks a day. And so it has to be super duper reliable. It has to work across, and these are not unpackaged objects. And so the shapes are weird and the surfaces are weird. And so a lot of the interesting research is around how do I build like suction cups that work across different surfaces, things that are reliable, things that give me sensing at the tooltip. and things that can keep on working even if the object is under three things or like in clutter or wedged in. Like that's what makes it hard. But the edge case is negative. Okay. Any questions? Okay. Navigation. This is an example from Waymo. I'm not going to go too far into it, but Waymo, as opposed to things like Tesla, etc., use a lot of LiDAR. And so they have like it's not it has a lot of learning in it, but it's not a purely learning-based approach. It's learning scaffolded with other things, right? And so they have definitely a learning-based vision system, something that does forecasting of other cars on the road. But they also have LiDAR, which is telling you what the obstacles are. And they integrate whatever the predictions are from the learned model, grounded in the sensors that they see around them, right? So it's some mix of model-based and learning-based system. This is slightly different. Like this, Waymo's like the car dynamics are relatively simple, right? You know how cars move. But the tricky part with a humanoid robot is it's hard to control the dynamics of the system. It's not just you go left or right or straight, right? You have to like coordinate all the limbs to do things like this. And so, to design a demo like this, which is the parkour demo, like the secret sauce here is that they're really cherry picking their demos. This doesn't work on all courses everywhere. It doesn't even work every time, right? But what they do is they instrument the world really heavily. So they don't really deal with vision. They have like something that tells you where everything is. They have a fixed set of courses. They plan where the footsteps go. And then they use these kind of trajectory optimizers or like NPC type controllers in order to tell you how to move your limbs to get there. Right? And so the cool part is that they essentially use a model of the humanoid and its context with the world in order to plan how to do things. But the caveat here is that it doesn't really generalize to a new course. It doesn't really generalize to a new terrain, right? And so since then they've moved on to more learning-based things, but this particular method is largely model-based. But on the like a big revolution has been using reinforcement learning for locomotion. And so a lot of it has been basically building on this framework called I6M, I6M, right? Like this weird thing is essentially thousands of robots spawned in parallel, right? And you're practicing how to walk with them using reinforcement learning. And you do it across many, many different terrains, many, many different appearances of the ground and so on. And then the cool demo from ETH, where they took something that is purely trained in simulation, and then they took it for a walk in the Alps, right? And so the cool thing is like you're seeing these terrains which you've never seen in the real world, you've only seen in simulation. But if you've seen enough of them in simulation, you can hopefully generalize and do better in the real world. And so what's really cool, like in this particular demo, there's still someone controlling it with a joystick, so it's not doing full navigation, but it's dealing with all the terrain by itself, right? And so a similar set of techniques has been like more recently applied to humanoids. So the things at the bottom here are fully learned, not model-based, right? So it's like, again, you just pre-train a lot in simulation with reinforcement learning. And then you can deploy things like if you recognize this is the Sue from Cristiano Ronaldo. They can like copy particular motions. And the cool thing about this is that you can apply it to new tasks, new motions easily. You don't have to like hand program anything. You essentially just specify new reference motion, train a bunch of simulation, and it transfers pretty well. The caveat is that it doesn't work everywhere. It doesn't have guarantees. It doesn't really work for manipulation that well. So there's still lots to do, but it's pretty cool to see the progress. The other cool thing is, if you look at this video, it's like pretty robust to perturbation. You're like throwing boxes at it and stuff. And so generally these are not open loop controllers, they're closed loop controllers. So they have feedback. So even if you put disturbances, they recover and do better. And lastly, this is the demo that came out like last week. It's called GR Dexter. But basically it's a demonstration of using these kinds of vision language action models for dexterous manipulation with robot hands. And so what they're trying to do here is they're trying to take a vision language model and get it to control all of the fingers of your hand, right? And so you can get it to like do reasonably precise things, right? Like do knitting and picking and twisting. And they didn't do anything fancy in the sense it was a vision language model with lots of data from hands. They did a good job of engineering. Methodology-wise, it's relatively simple, but kind of shows what the possibilities are. And it does generalize somewhat to new tasks and new settings, but not amazing. Okay. Why should we care about robotics, right? One is because you're in this class and you have to care. But I think the reasons I care often are societal impact, right? I think it has impact in a very real, tangible way. And you can have robots that are butlers, of course, but you can have robots that do surgery and that do search and rescue, that are prosthetics and do assistive care. So I think there's a lot of potential for societal impact or driving. Um, a lot of money in robotics, right? This is actually a year or two old. If you look at like the VC market right now, I don't know if Charles is here, but basically the VC market in robotics is blowing up. Like they're throwing money everywhere. And so there's a lot of money to be made and a lot of cool products to be made. And lastly, robots still do stupid things. And so there's still a lot of room to innovate. So if you want to do research or you want to build new products, there's a lot of space to innovate, as opposed to other domains that are closer to being solved. Okay, that's cool, right? But we didn't come here to look at demos. We came here to learn how to build these robots. So how do we build these robots? We need a framework, right? So we need a framework and a set of tools to kind of start building these robots. And so we're going to use a framework called Sense Plan Act, right? And so as the name suggests, there's going to be sensing. Given the sensing, you're going to have planning. Given the planning, you're going to have acting, right? And so we're going to try and instantiate what Sense Plan Act is in the context of an example, and then trying to build the formalism we need to like get each of the pieces, right? Okay, so the agenda for today is we are going to talk through the design of a robotic system, right? So we want to build a mobile robotic system. We're going to talk through what are the elements needed to build a mobile robotic system, right? And the rest of the quarter is just going to instantiate each of those, right? And so we're going to do it for cars throughout the quarter. But today we're going to take a more fun example. We're going to talk about helicopters, right? And we're going to talk about helicopters and then doing missions and try to translate those things onto a car. Okay. So what we're going to have with the flying vehicle is a mission that looks something like this, right? You want to take off somewhere and you want to get to some target location. You have a rough idea where you want to go. You don't exactly know all the obstacles and the wind conditions and everything in between. You have some rough idea. And so you have to use your onboard sensors in order to figure out how to get from one place to another while not crashing, not running out of fuel, not dropping any of your payload, not violating any of the FAA rules, right? And like obeying the dynamics of the helicopter. You can't just like go upside down. Okay, so these are videos from a real helicopter mission, but we're going to try and design a system to do that, right? So the mission kind of goes from takeoff, we have to respect power constraints, to moving, where you have to avoid sensed obstacles and deal with all the adverse weather conditions you might have in the way, and touchdown, which is often the hardest part, which is trying to figure out how exactly to maneuver under the weather conditions to get to a particular site. So generally, the problem statement is that you're given a start, you're given an end, right? You're given a start and a goal in terms of the coordinates. You're given some list of no-fly zones. You're given some rough terrain map. That terrain map could change over time, right? And you're given some set of onboard sensors, like GPS, laser, cameras, barometers, something to measure the wind, right? And your goal is to minimize the time it takes to complete your mission, point A to point B. Okay? But you want to do it under a certain set of constraints, right? So you want to get from A to B as fast as possible, but you cannot enter the no-fly zones. You cannot exceed the limits of the vehicle because you're going to be unsafe, so you can't allow it. That's kind of the problem that we're going to try and solve. Make sense? Nothing too complicated. Okay, so we're going to try and cover two different ways to do this, right? The first is going to be the model-based way. And so let's start with a blank slate, right? So we have the problem statement. The problem statement has input sensors. Output is we have to control the like pedals, the stick, and the lever of the helicopter. And our autonomous system is going to go from all it has is the sensors, and all it has to output is the actuators. So question for y'all is how do we build an autonomous helicopter? Like how would we start? How do you approach this? That's a hard problem, right? I have to get a helicopter that flies and has guarantees and is reliable. And how would I build such a system? Yeah.
Well, figure out how it works yourself.
That's right, yeah. So the first thing we're going to do is kind of use our own knowledge about how helicopters work, and try to bake that into the design of any autonomous system, right? And so we're trying to figure out what the control system is to go from sensors to actuators, right? That's the point of most autonomous decision making. We're going to start with our own knowledge of the system, right? So we're going to start by defining what we call a world model, right? Our world model is super overloaded word. People in different communities use it differently, but we're going to use it very literally. It's basically saying it's a model that describes how the world works, right? And it's like, in our case, it's going to be something that we write down. We're going to define the model. We're going to define how the helicopter dynamics work, but you can also learn it from data, right? But generally, we're going to start, like if you want to plan with a helicopter, you need to start with a model of the helicopter. And so the reason it's called a model-based system is because you start with a model, right? And then you try to make decisions with that model. Are there pros and cons you can think of using a model? It might not generalize, yeah. Although arguably physics is the most generalizable thing we have, but we may not generalize to all conditions. Good point. Any other challenges we might have with the model?
Expected edge cases.
Expectation. So inherently, the reason it's called a model is because it's wrong. Like a model by construction is wrong because it's just an approximation of reality, which means that every model is wrong, which means that we have to find a way to deal with the errors of every model. So edge cases could be one, others could be unmodeled effects, right? You're not modeling every particle of wind, and you're not modeling turbulence perfectly. So you're gonna like see things that you don't expect. So you got to deal with it. Okay, so we'll think about those things. But we're going to start with just a helicopter model, right? Once we have a helicopter model, like a helicopter model is going to tell us like how if the helicopter was at some state of the world and you apply these controls, how would the helicopter move? Right? But in order to see the model, you need to know where you are right now. Right. And so the second piece we need after world model is something that tells you how to see the world model, how to tell you where the world model is, like where should the world model make predictions, right? And so that's what's going to be our state estimator. And then the last bit is once you have your world model and you know where you are, you have to make decisions in that world. Right? So world model just tells you how the world works. It doesn't tell you how to make decisions in that in that system. Right? And so we start with a model of how the world works. So how the world works says if you're at a state, you take an action, you get to some new state, right? But it doesn't tell you what action should I take to get to some desired state, right? And so the process of decision making or planning is often trying to find what actions do I need to take to satisfy my mission constraints, minimize my objective while obeying the dynamics of my system, right? So this third box is planning, middle box is world modeling, and the first box is state estimation. And so the three parts we're going to kind of think about here, and that's kind of the first three modules of your class, are world modeling, which is telling us how the world works, right? So we're going to talk about a helicopter here, but we'll also do it for the car in this class. Right? We'll then do estimation, which tells us that if I needed to figure out how to make decisions with my model, I need to know where I am. So I need to give an estimate of the state of the world, and we'll talk about what a state is. And then the third part is once I have the state and the model, how do I invert it? Like a model tells me how the world works. I need to invert it to figure out how to make a decision. Right? I don't care about how the world works. I just care about how to make a decision. So the key is that even if the way the world works is a little bit wrong, you can still make the right decisions. Okay, any questions? Any concerns with this framework? Good. Cool. All right. So there's lots of ways we can model a helicopter, right? But we're gonna try and use our knowledge of physics, right? So we're gonna first try and define what a world model is, right? What is it predicting? So the variables it's gonna model are things like the position of the helicopter, the speed of the helicopter, the payload distribution, and how they change, right? So it's saying that if you know the current position, speed, and payload, you apply some controls. What is going to be the next position, speed, and payload, right? Under the physics of the helicopter, when taking into account obstacles, other aircrafts, wind, weather conditions, beyond that, like pressure, like that, right? Or you can even think about things like your helicopter might have some damage. You want to factor in your damage into how the helicopter moves. Right? And so what your world model is going to, like the things up here are kind of what you define as your state, right? And this is kind of what your world model is going to predict. So it's going to use the physics of the world in order to predict the next state. Right? So you can always think of world model as something that takes in state and action and predicts next state. Right? And in our current definition of a world model, we're also going to predict things like cost, right? So there's a bit of a disputed point, like whether costs and these kinds of things go into the world model or not, but I wouldn't worry about it. It's just like something that tells you, like, how good am I doing on the mission so far? Okay. So we can read these textbooks to figure out how helicopters work. Like lots of people have done lots of modeling on helicopters. But often what you really care about is a model that goes from states and controls to next states and costs. And you use a simplified model of the world, right? So like with helicopters, often you like treat it like a unicycle, which is kind of weird, right? But you essentially pretend that your helicopter is a unicycle. Like you can't go sideways, but you can like travel in curves like that, right? And so you plan with a simplified model, and then you correct for the simplification with planning and control. But the point to make here is that I can design models at different levels of complexity. Often for decision making, you choose a simplified model so that you can make decisions faster, and then you correct for errors in that model after the fact, right? So it's just that if I model every single particle and how it moves, it's going to be super intractable for me to make decisions in real time for a helicopter. And so a key engineering lesson in most decision making is you're never going to plan with a true model. You're always going to plan with a simplified model, right? Okay. Does that make sense for a world model? So like there's the true world model, which I don't have. There's an approximation that I'm going to make. Right? And all I want with my approximation is that it captures how the world works well enough for me to make decisions. Yeah. Okay. So that's part one. Okay. So we're going to start with the world model, but the next part is, okay, I have my world model. It doesn't do me any good. I need to make decisions, right? So the process of making decisions with the world model is saying that I want to do planning and control, right? So planning and control are like a little bit confusingly different terms, but the real difference between them is that planning is a lot more coarse and global, and control is a lot more fine and local, right? So planning is saying I want to take my helicopter from point A to point B. I want to avoid that obstacle. I want to avoid that no-fly zone. How do I plan at the like 10-meter resolution where to go? So I'm not planning at the level of, how my blades move. But instead I'm planning at the level of what are my waypoints every 10 meters. And then I want to figure out things like how do I produce smooth paths? How do I produce paths that avoid the obstacles, satisfy the constraints, and so on. And then control is saying once planning has given me those waypoints, how do I follow those waypoints really damn well, right? And you need control because your model is wrong. Right? So if your model is wrong, then you have to like correct for things that you are going to make mistakes with. And so the process of planning is trying to figure out how to go from A to B while satisfying constraints. The process of control is trying to get to each waypoint without deviating under the dynamics of your system. Right? So just one is way more global and one is way more local, but you'll see that like the methods start converging at some point. Like often control methods can be used for planning. Right? So they're different, but kind of the same. Okay, so maybe one silly question is like, if they're different but kind of the same, is why shouldn't we just do it all together? Why shouldn't I just like, why do I need to separate these to two levels? Why don't I just like plan the whole thing at once? Yeah.
Events that happen.
Unpredicted events are to deal with, but I think unpredicted events may happen in this case too. Right? Yeah.
change.
If you want to change, yeah, some modularity allows you to change one part without changing the other. That's fine. Are there other reasons? So maybe one way to think about this is imagine you were like thinking of how to go from here to, Boston. And would you plan at the level of your like arm motions the whole way? No, right? Because it's like it's going to like if you think about the decision tree is going to blow up to be exponentially huge. And so essentially what hierarchy, there's essentially all that this separation between planning and control does is introducing a hierarchy, right? So you're saying that I'm not going to plan to go from here to Boston at the level of my joint motions the whole time. I'm not going to figure out which joint motions get me from here to Boston. I'm going to assume that I'm able to get to different waypoints and then figure out which waypoints get me from here to Boston, and then think about how to get to those waypoints, right? And so hierarchy takes a complicated, big decision tree and splits it up into a much more tractable decision tree. So the tractable decisions are, I assume that I can get to waypoints. Which waypoint should I take? And once I know which waypoint I should take, then I think about how to move my limbs to get to those waypoints. Right? What's the pitfall of doing this? Like, where could this break? That's right. Yeah. So you've introduced this hierarchy. And so you kind of assume that you will plan with waypoints that you can get to. And so you need to make sure. So often there's this thing Sid is going to cover called dynamic planning, which is saying, how do you get to waypoint, like how do you make sure that the waypoints that you choose are dynamically achievable, right? Like you might have things that are not achievable, and then your whole hierarchy breaks. And so you need to be careful when separating things hierarchically, but you never want to plan at just like one level of resolution. It's pretty inefficient. Okay. So if you kind of think through the planning problem, so planning is an optimization problem, right? It's not always cast as an optimization problem, but really it's an optimization problem where you're trying to search over a sequence of actions or waypoints, which minimize some cost function. Right? So the cost function could be time, it could be fuel, it could be, tilt, it could be whatever you define. You're going to use the world model to do planning, right? The world model tells you where your robot can and cannot. And you're going to make sure that in this process, you're not violating constraints. Right? And so if you ever want to think about planning is just this problem. Right? It's just saying you want to get from A to B. You want to find a sequence of actions that minimize the cost while not violating constraints using the model of the system. Okay, so we're going to use this unicycle model or you're going to use this, we're going to use the bicycle model for the car, but like the reason is that a car has two sets of wheels and a helicopter just kind of turns on a single wheel kind of. So for a helicopter, you use a unicycle model, and for the car, we're going to use a bicycle model. We're going to use a simplified model to do planning. And then if you think about control, the problem of control is saying my helicopter is there. Planning has told me that I got to go here. But due to wind or poor modeling of my helicopter, I made a mistake. And so I need to figure out how to fix my mistake, and I've got to figure out how to change my controls to fix that mistake. So we're going to get into this in lots of detail, but what is one way you could fix your mistake? Has anyone encountered ways of like doing control? Like think about yourself. Like you're driving, you like veer off, you veer off the path. Like what do? You just veer back, right? You just veer back. So essentially, it's often helpful to think of control very geometrically and intuitively. All you're doing is you're trying to do corrections based on what your errors are, right? So a lot of control we're going to cover the area called feedback control. So you're going to look at the feedback between what you did and what you wanted to do, right? And that's going to be what the signal you need to correct for your error, right? So we're going to cover something called PID control, which is essentially trying to say, this is where you want to get to, this is where you were. How do I change my controls to get closer to where I wanted to get to, right? Does that make sense? Okay, so lots of reasons that your robot will not do exactly what you wanted it to do. Disturbances, model errors, sensor errors, right? And your job is to, like, there's two ways of dealing with this. One is try to make your model so damn perfect that it'll work all the time. And the other is to say, accept that you are going to fail at modeling things perfect, and then just fix it while executing. Right? And so the primary principle in control is that, there's some things where you have just one shot, one shot at doing things, and if you fail, you fail. But in most control systems, you can like make corrections, right? It's not just like you're throwing a dart and you're done. It's more like you're driving, and at every step, you can keep making corrections, right? And so the principle of feedback control is that you have the opportunity to try many times and make corrections. And you're going to account for any of the errors that you have, right? So we're going to try and think of this largely in terms of path following. So you have a path to follow or a waypoint to get to. How do I correct for my robot motions to get back to a particular path? Now, the reason to do that is many, right? You could have, but like really most of the reasons kind of boil down to an unmodeled effect, one way or another, right? So like one thing that I always find useful to think about is like the connection between stochasticity and partial observability. It's basically like, what is noise? What is stochasticity? It's just anything that is an unmodeled effect, we kind of shove into stochasticity, right? So if I could model the world perfectly, then it's near deterministic. But whichever thing I cannot model perfectly, I shove into stochasticity, right? And so the more approximate your model is, the more stochastic it is. And so you can kind of think of this as dealing with model error. You can think of it as dealing with stochasticity, but they're not that different. They're kind of similar things. Okay, so that's what control is. So that's the second part of our system. We've talked about a world model, right? We've talked about plan and the controller. The last part is what we're going to call state estimation, right? And so state estimation is saying, okay, a model is taking in state and action and giving me next state. But how do I plan if I don't know my current state, right? And so the challenge of state estimation is saying, you have the model that tells you how the world works, but how do I know where I am right now? Right? And so why is this tricky? Like, why is this not trivial? Like, I can measure where my helicopter is. Right? Why isn't it trivial? Lots of noise. Right? You have your GPS and your LiDAR, but there's like a snowstorm and there's rain, and your sensors can't be trusted. Never trust anything. That's the lesson of this class. So what we're going to try and do is we're going to deal with our noisy sensors, and we're going to try and figure out how to use those sensors, not trusting them blindly, but kind of build a probabilistic estimate of where we are in the world. Right? And so the reason it's called state estimation is that you're not saying that like this is the state. You're saying that this is what I think the state is going to be. Right? And so the difference is that one of them is saying like, I know for sure that this is the state. And the whole principle of probabilistic robotics is saying that I don't know for sure where the state is. This is what my belief is where my state could be. Right? And so if we think about like the things that we need for our world model, right? There's a bunch of these things, right? There's where is the robot in the world? What's its position? What are the obstacles? What are the no-fly zones? Where are the aircrafts? What are the wind conditions, right? And you have different sensors that give you some estimate of each of these, but each of these different sensors have different like, noisiness. Like for instance, GPS might drop. Laser is, affected by particulate in the world or by surfaces that reflect light weirdly. Radio again has communication errors, right? And so we can't really trust any of our sensors. So if you think about like any of this state estimation problem, you're getting lots and lots of sensor readings, and you have to integrate all of those sensor readings to get a reasonable estimate of the world. If we forward through this guy, you see, a rangefinder looks something like this. You're trying to figure out where the obstacles are in the world, but it's never super duper clean, right? You might have things interfering with each other. You might have things that just don't bounce back. You might have things that your sensor fails sometimes, right? And so you'll often have examples that look like this, right? So let's consider the helicopter flying through a snowstorm. this is kind of what a sensor reading looks like if you shoot lasers at the ground to see what the terrain looks like. And pink is saying it's an obstacle, and green is saying it's not an obstacle. Right? So you can see that it's like lighting up way more than it should. And that could be because the laser beams interfere with each other. It could be because the snow kind of bounces things back even when it shouldn't, right? And so if you look at any one snapshot of a reading, it's often like you've got lots of spurious positives, spurious negatives, right? Whereas if you properly make this probabilistic, so you take many, many different readings and you integrate all those readings to get an estimate of your state, it looks a lot more sensible. So you like, if you just take one reading and pretend that's the ground truth, it's going to be way overconfident, right? And so you want to make sure you build a belief of what your state is given the data from your sensors, right? So the problem of state estimation is figuring out what is the state of the world given my sensor readings, right? What is the probability of the state of the world given my sensor readings? They're trying to get a belief. Okay, so essentially that's going to be the first module of this class. It's just going to be figuring out how to get P of S given sensors. That's it. Okay, so that's kind of the construction of an engineering system. We have three parts. We have the world model, right? Define how the world works. The second part is planning and control. We try to do things hierarchically. And then we have state estimation, which is saying don't trust anything, don't trust your sensors. You have to build a belief over what your state might be, given you model noise in the sensors, right? So you have to like account for the fact that the sensors might be noisy. Okay, so what are some lessons we learned from this exercise? What are some things we can take away? Never trust anything. Never fully trust the model. Anything else? What else comes up? There's a show I used to like to watch called House, and the motto is everybody lies. So it's true about robotics. Lots of noise. Yeah, you have to explicitly model and account for noise. Yeah. So you want to be, and this is true about machine learning too, you want to be probabilistic as much as you can. The more probabilistic you are, the better you deal with noise. The like more deterministic you are, the more you are to make an error and keep making it. That's why generative models work so well.
Important to have a range of sensors for your.
Important to have a range of sensors. Yeah. Because they each might have complementary effects and deal with uncertainty differently. Right. Okay, so here's some things that I took away, right? So you wanna, like, one of the lessons of model-based control is that we thought about world modeling, and then we said, okay, given a world model, how do we plan? And then given a world model and a plan, how do we seed the world model, right? So we took the big problem and we broke it down into little parts. And we'll talk about how there's some pros and some cons to that. But generally, the lesson of model-based control is don't think about the whole problem at once, break it down into pieces and consider them one at a time. Second is plan with simple models. So like there's always a trade-off between computational complexity and accuracy. And often you want to err on the side of simpler model and account for the model error in a different way. Not all planning is made equal. Not everything has to happen at the same flat resolution. Hierarchy is a good thing, right? So like it's true in machine learning too. It's like hierarchy can often make everything easier. And lastly is like when you have error because of sensor noise, because of model noise, you're going to use feedback to correct it. Right? So the fact that you get feedback from the world, it's not like a system where you do something, it goes into the void. It's like you do something, something happens, you get feedback, you can correct it. So those are 4 lessons that I took. Okay, so that is the design of a model-based system. That's going to take us from sensors to actuators. And so once we have sensors, we estimate the state. Once you have the state, you can see the world model. Once you have the world model, you could do planning and control. Control will give you actions. Actions go on the helicopter. I repeat. Right, so like every single, 1/10 of a second, we do this whole loop, right, in order to make decisions. Okay, so, we talked about helicopters, but unless we get a big grant from Bill Gates, we're not going to get any helicopters for our class soon. So we're going to think about cars, right? And so do the same lessons apply to cars? And so here's an example from 18 years ago. This is a car called Boss from CMU. And it is the winning entry to the DARPA Urban Challenge. Has anyone heard about that? It's a little old, but it's basically kind of what spurred Waymo and the self-driving revolution, right? There's the DARPA Grand Challenge in 2004, I think, and the Urban Challenge right after. But the point of these challenges, it's kind of like a DMV test, right? You have this car, it has to it's parked somewhere, it has to go from A to B, it has to navigate while following the road rules and avoiding, unforeseen obstacles, other cars in the road, etc. This is certainly much worse than a Waymo, right? But this is in 2007. So, pretty deep learning and everything else. And so if you kind of look behind the hood of this kind of car, you'll see that it actually uses a lot of those planning, state estimation, control techniques we talked about. Yeah, it did go onto the road and do like kind of reasonable things. Would you sit in this car? Maybe not, but was it pretty good for the time? I think so. And so there's actually a nice paper, you can find it online, which like details the design of the system from start to finish, right? It's meant to be like open source. And so you can look through this, and it gives you lots of nice details. It's a little before my time, so let me know what you find. But if you look at the design of such a system, you can see that it has a world model. It has like those little lines are like possible paths that it might take. You're going to do lines like that for your car in this class too. You have possible paths. You're going to predict, how the world will evolve. You're going to predict how your car is going to move. You're going to estimate where your state is going to be from these noisy sensor readings. You're going to plan globally how to get from A to B while avoiding obstacles. You're going to have a local planner which corrects for drift in your wheels. And then you're going to have something which deals with safety and make sure that all your actions are safe. So that's kind of like, it has all the elements that we talked about. And so like a lot of the lessons do actually translate over. And there's not just like in 2007, if you look at Byron Booth's company, like Overland, which I talked about last time, they're using a similar stack for autonomy off-road, right? And so it applies in 2025. Now, the cool thing here, which is like often the focus of a lot of the efforts in Waymo, like the learning efforts, are you have to deal with other drivers and you don't know what their intent is, you don't know what their style is, you don't know what errors they're going to make. And so a big challenge in driving is forecasting, right? You have to forecast what the possibilities are. And then you got to plan for all contingencies, right? So you got to plan in a way that allows you to like have an option if people do things, right? And so like two difficult problems that you might want to look up are forecasting, right? And contingency plan, like planning in a way that allows you to have options if things didn't go your way. There's a fun blog post from Waymo, which I mean, it doesn't give you that much details to be honest, but it kind of talks about a bit of their tech stack. So it does have a significant element of learning in it. I actually hid this thing behind, but basically they're using a bunch of driver data to seed their model. Then they do some reinforcement learning on it. But then they put it through a learned planner and a critic in order to like verify whether things are safe. And when you like look at their thing, you can see that they're like kind of forecasting their own path, predicting where people are going to move, and using that to like make sure you're safe all the time. So even when people like fall out on the road, etc., they're able to like slow down, plan around it, and so on. So there's lots of elements of learning in it, but it's also using like a safety layer, a planner, things like that to make sure you're reliable. I can send out the blog afterwards if you're interested. And so they apply in the musher cars, which are a lot less expensive than the Waymo cars. Well, let's hope it works this quarter. But I think it will. I think it'll be a lot of fun. Okay, so the sense plan act framework is saying sensing for measurements, planning for models, and acting in the real world, right? Now let's think about like we've talked about why sensors are hard, right? Like they're noisy, prone to drift. But if you think about like control, like here's like a humanoid system which has like a pretty janky system, right? But you can get even these kinds of systems to walk if you use feedback control in the right way, right? So a system is pretty wrong, has lots of errors, but you can still get it to walk if you use feedback control and you have perturbations. And here's an example I find kind of informative for planning. So the problem is you want to move this little green thing over to like some target, but you can only slide and rotate the green thing. It cannot hit any of the obstacles in the right? And so you can go X, Y rotation, like it's a 3D space of motion. right? But you have to move it from A to B while not colliding with anything else. And if you actually look at like the space you have to navigate in 3 dimensions with the obstacles projected into that space, the space looks like super duper nasty. It looks like that. So if you're moving just in free space and I could like go, there's no obstacles, I could go anywhere, then it's an easy problem. But if you look at like the problem you're actually solving, you're navigating this super nasty non-convex space. It's like not an easy search problem, right? So like I think this figure is perhaps like the space you have to navigate is through this like super complicated non-convex shape in configuration space, in the space of configurations. So we'll go into the details of that, but it's harder than it looks, even for this silly problem. So imagine for a humanoid. Okay, so robotics is often the problem of integration. So you'll see in all your homeworks, you can do state estimation, but integrating planning into it is going to be hard. And once you've done state estimation and planning, integrating control into it is going to be hard. So you want to make sure all the pieces work together. Okay, so that's one way of doing it. What's a different way? Are there other ways we could do this, which is not model-based? How else would you design an autonomous decision-making system? Huh?
Random movements.
Random movements, but with a helicopter, I don't know, man. I don't know who's going to give us a helicopter to do random stuff. Are there other ways of doing this?
Yes. Reactive.
Purely reactive. But how do you decide how to react?
Yes, I mean.
Yeah, you need a model. So when we say model free is a bit of an overloaded word, but I'm referring to things that are learning based, right? So one way to learn how to fly a helicopter is to watch people fly a helicopter 10,000 times and then just copy how they do it, right? And so you're not so much copying the model, you're copying the policy. You're copying like how they actually act, right? And so, the typical model-based planning setup is you have state estimation, model it, the planning and control, then you act, right? But the paradigm of end-to-end learning, right, is saying that like, fuck that, we're just going to go from sensors to actuators. We're just going to use a bunch of data and big neural net, right? It's kind of, I mean, there's going to be caveats with it. We shouldn't use it everywhere. Certainly not a helicopter. But the paradigm of end-to-end learning is saying, let's try and replace these engineering systems with data. And in certain cases, that can be effective. But it's kind of like, it's trying to say, these engineering systems act together to take in some cause, give you some effect. Let's try to mimic, given a bunch of examples of cause and effect, cause and effect, cause and effect, let's try to mimic that. Right? And so you're just going to use a big neural net and gradient descent. It doesn't have to be a neural net, but you could use a learning-based system. When you say end-to-end, you want to go from sensors to actuators. And so, the example in the helicopter would be you fly a bunch or you watch a bunch of logs of people flying. And then you say that, okay, when you saw these sensor readings, you did this. When you saw these sensor readings, you did this. You saw these sensor readings, you did this. And then you try to copy that so that when you get new sensor readings, you know what to do because your model should generalize, or your neural net or your learned model should generalize. Now, why is this why might this be a good idea or a bad idea? That's right. You often don't have enough data about the negatives, especially. And so if you ever get into an eventuality, you don't know how to recover. Good point. What are other things that make it good or bad? Like, why shouldn't I just machine learning everything? But might be hard to reverse it. There's no interpretability. So something goes wrong, you don't know where to attribute it. Other concerns. Yeah. CFD. There's very little guarantees with most machine learning methods. Yeah. You're not, I guess you could get new data with new flights, but it's the amount of data is not huge. Okay, so there's maybe some reasons to do this or not do this, right? So like some good reasons to do this that you all have mentioned is when you have a modular system, right, you might have your state estimation make some error. That error may not play perfectly with planning. That planning error may not play perfectly with control. Right? So the modules are meant to hit targets, but they're not meant to play well with each other's errors. Right? Whereas an end-to-end system is just going from, it's like doing the thing that you care about. Right? You can avoid hand designing what states are. So like, for instance, you want to deal with like rice. Like, what is the state of rice? Right? Whereas like, you could just go from pixels to torques. And it often is more performant if you have enough data. But the challenges are that you need a shit ton of data, which is often hard in many applications. It's hard to get guarantees and interpretability. And because you're not modular, like you trained on something, it's not clear if you can use it for something else, right? And so learning has its place, but it's not useful for every system, especially not safety critical systems. Cool. And we're going to cover two types of learning in this class. We're going to cover imitation learning. So you can learn things by copying other people, right? And then we're going to cover reinforcement learning, which is learning through experience. So imitation learning is largely copying helicopters with people driving helicopters around. And reinforcement learning is imagine you let the agent fly the helicopter itself and figure out what works and what doesn't work. And so that's going to be the structure of our class. We're going to start with state estimation, then we go to control, then planning, then learning. Right? Cool, right? I think we're at time. Thanks all.